Welcome to math class. Today we are continuing on with the Math Makes Sense 9 textbook, Unit 2, and we're covering Chapter 2.4 today, the first of our exponent laws. We're actually going to start, let me bring that back up just in case. We're going to start looking at a couple examples on page 74. There's a couple of easy rules that we're going to be using in this lesson, but before we cover that, we want to actually look at the theory and the reason why we're able to use those rules. So they give us an example of negative 7 cubed times negative 7 to the 5th power. And we have to solve it. Simplify it so that we get one exponent number that we can work with from there, an easy number that we can essentially punch into our calculator. So the way that we're going to do that is we're going to actually show you why and how we can solve this easier, but we're going to show you the simple way by doing the hard way first. So what I'm going to do is actually break each of these exponents into their individual parts. So we have negative 7 to the 3rd power times negative 7 to the 5th power. So negative 7 to the 5th power. Now, if you notice here, I wrote a multiplier sign in the middle. But the question is, do we really need it? If you notice, every time I've got a number in brackets beside another number in brackets, this is representing multiplication. So this is essentially just an unnecessary piece of writing that we put in there for no reason. So we're going to rewrite this, if I can say, without that in the middle. Do that right? And what I'm left with is negative 7 written out that many times, written out 8 times to be specific, which, as we know from our last couple units, we can actually rewrite as negative 7 to the 8th power. If you're observant, or you're paying attention to this video, what you'll notice is that the 8th power is the same as the 2 powers up here added together. 3 plus 5 equals 8. We have a very simple rule, and we'll demonstrate it later, but it's any time we have numbers with the same base that are being multiplied, if they have exponents, we can add them together every time, as long as our bases are the same. So let's take a quick look at what happens if we're then dividing. The example they give us for dividing is 8 to the 7th power divided by 8 to the 4th power. We can also rewrite this as a fraction form. So we have 8 to the 7th power divided by 8 to the 4th power. Same way we showed you on the last step with multiplication. We are going to show you or get to the shortcut, but first we're going to show you how it works. And it's pretty simple to the same method. So we're going to rewrite this out into its repeated multiplication form. Oh, no, sorry, that's right. 8 to the 7th over 8 to the 4th. Now, we've seen this before in division. If we have things on the top and bottom, we can actually cancel them out. So we are going to match up. We take 1 8 away from the top and bottom. Take another one away from the top and bottom, another one, and another one. So now what we're actually left with is just 8 by 8 by 8. which we remember from our last unit can be written as 8 to the third power, or 8 cubed. So what that means for our shortcut is anytime we are dividing, if we have numbers that have the same base, we can actually minus the exponents. Okay, so if we have the same base and there's exponents involved, dividing is going to get us to actually minus the exponents from one another and make it simpler. So those are our rules. So let's take a quick look at a couple examples on the next page and see what those rules look like in action. So if we look on page 75, they have a couple of examples up at the top. So the first one they give us is 6 to the 5th times 6 to the 4th. After seeing our last little demonstration there, we know our shortcut. So instead of doing all the extra writing out, I'm just going to look at the exponents. Since they have the same base, I'm going to add these exponents. So now I get 6 to the 10th power. If it makes it easier, what you can also do is write it out in a fraction. 5 plus 4 in the exponent, or sorry, not as a fraction, write it as in mathematical equation in the exponent spot. So 6 equals, oh, sorry, terrible math teacher doing mistakes for all of YouTube to see. 6 to the 9, sorry, 6 to the 5 plus 4 gives us 6 to the 9th power. The second example we see there on that page is negative 9 to the 10th power divided by negative 9 to the 9th power. Sorry, ooh, apparently I can't read today either. To the 6th power. Both of these powers have the same base, negative 9, so I'm able to negative 9 to the 10 minus 6. So I'm able to simplify, so I get negative 9 to the 4th power. Very simple. Down on the, on the next page, page 76, they show us how we can use our exponent laws once we're starting to mix them with other equations. So essentially we're retouching on how we use it within the order of operations. So on page 76A, right at the top, they have 6 squared plus 6 cubed times 6 squared. Now, always, 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 we have to keep in mind our order of operations. BEDMAS. Looking at that, we have to go step by step. No brackets in here. We do have some exponents to deal with. We have multiplication to deal with, and we have some addition to deal with as well. This is where we have to get a little bit cute with the way that we think about our order of operations. Technically, I'm supposed to solve my exponents, each of these, before I multiply. But because we know our order of operations, I know that I have to multiply before I add. I'm also going to take this opportunity to simplify it for myself. So I'm going to actually rewrite this equation as 6 squared plus 6 times 3 plus 2, sorry, because I've got multiplication with numbers of the same base, so I'm going to add the exponents. So I actually get 6 squared plus 6 to the 5th. I have not actually solved my exponent. What I've done is simplify It's an important distinction. I still haven't solved my exponents. I just know with a couple of the shortcuts I've learned that multiplication sign gives me, I can make this easier upon myself. I cannot do anything with my exponents with an addition or subtraction sign. My order of operations is very, very clear. I have to solve those exponents long before I get to addition or subtraction. So I'm going to solve them. So 6 squared is going to give me, 36. Well, I'm not sure why I'm trying to squish this in. I've got all kinds of space to work with. Right. Equals 36 plus 7,776. Now we have to add these together. This equals 7,812. That's actually a very, very different answer than 6 to the power of 7, which is actually 279,936. Very, very, very different. So we have to make sure we're following our order of operations. We'll do one more quick example on there and then we'll move on. So for the next question on that same page, give myself a little bit more room. They give us -10 to the 4th, square bracket here, -10 to the 6th divided by -10 to the 4th, square bracket, minus 10 to the 7th. So once again, following our order of operations, we're going to start with the brackets. So I'm going to deal with what's going on in there. So we know we've got a shortcut we can use, so we're going to rewrite this whole equation. Remember, going step by step. So I've got -10 to the 4th times, using my shortcut, I can go 6 minus 4. So in here I now get -10 squared minus 10 to the 7th. Exponents, I have to deal with them, but before I do that, I notice that I have numbers with the same base, so I'm going to simplify. What they're essentially doing here is, or what they are doing, not essentially doing, is multiplying. So I know that I can actually add my exponents. So I get -10 to the 6th minus 10 to the 7th. Now, what I definitely cannot do here is there is nothing I can do with these exponents. So now I just have to solve it. So -10 to the 6th power gives me 1 million minus 10 million equals -9 million. And there we go. That's how we solve exponents using our exponent law shortcuts within the order of operations. See you in class.